All right, guys, welcome to another CUDA education episode. This one, a quick one today. Basically, I just wanted to show that there are um, there's a counter I implemented where you track the submissions and the completions of work, right? So we're dealing with the render function. Let's just run the program for now, and you could see that we are tracking submissions and completions, both on the graphics side and the compute side, right? We're tracking them. Notice that the compute in flight basically is 0, which is generally the difference between submit and complete. There's like an intermediate step, but for the graphics, there is a difference. And I mean, just because of the way it's calculated, it's -1, but we know that to be 1, right? So I attempt to track this stuff, right? And I made some modification to the code. And basically, remember we have our render function here. This is our render function. Okay, all of this bad boy is our render function. And I implemented a sync stats compute complete count. We count here for the compute stuff. We count here for the compute completion, and we count here for compute submit. Notice that the compute submit is right after the VKQ submit, right? So VKQ submit, compute submit counter is incremented. Also for the, obviously when we're finished waiting for the fence, that means that compute has completed. So as soon as we're finished waiting for the fence and the processor can continue, we increment the compute complete counter, right? So that's for the compute side, and it's similar for the graphics side. So we have wait fences for the graphics. Once the fence is waited on and we get a return, we immediately increment the graphics complete count, right? And similarly, when we submit graphics work, we increment the graphics submit count, right? Sync stats graphics submit count, right? And that's how we get our that's how we get this bad boy, right? That's how we get this guy. Again, we have a difference between the two, which we'll see in more detail in a second, because we have the graphics in flight. And you guys remember from our previous discussions that unlike compute, where you compute and then you submit and then wait for completion, and it's what they call a serialized process, right? For graphics, we submit, we complete, but also there is a submit frame step, right? I really don't want to misspeak too much on this, but basically there's a frame submission step. So we submit stuff, we draw it up, present to the screen, and then we complete, right? And that's why we get this -1. That's why we get this -1, right? But what I'm going to do is I'm going to slow this down a little bit, right? I'm just going to slow down our algorithm so we could kind of follow what exactly is going on, all right? So when we slow it down, right, and because I slowed it down, it gets, so the animation is still moving, but you could see there's a difference between submit and complete, and you could see that the in-flight accounts for that difference because you actually have to present to the screen. Notice for the compute stuff, there is no in-flight anything. It's just equally thing because the fences make sure that blah, 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 everything is in sync. But for the graphics side, we actually have something in flight. Okay, so that's why we have this -1. But I just wanted to implement this because I wanted to show you guys that, this is real stuff that's happening. And it basically ties together all that we have spent with with the render function, right? We have compute stuff, we have graphic stuff. The graphic stuff also has presentation stuff it has to do. And it also, we use fences to sort of manage these things because, we submit to the GPU, but like all of this stuff is managed on the, all this code is CPU side, right? So we submit work to the GPU, we submit work to the GPU, and then we wait for the work to complete, and then we resubmit more work. On the graphics side, we also submit the frame. So we have to draw stuff and then submit it to present to the screen, aka our monitor, right? And if we increase, well, let's decrease it first. Yeah, if we decrease the wait time, we're still gonna get our animation, but we are going to get it a little bit faster, right? So we're now up to 9 frames per second. It was a lot lower before, right? And you will see that if we do like 800, you will see that there is a difference. We're down to 1 frame per second, right? This will not pass for a class A game or simulation, but you get my point, right? And it would still fall on the sphere and everything. It would just take a lot longer, right? So I'm going to leave this counter stuff in. You basically have to add stuff to the base class. And then, you get this, it's a strut for the, where is it? Right here. Right, this guy. So you add a strut, sync stats, right? And it's part of the public class and all that, right? Vulkan example base, right? And that's the lesson for today, guys. So I've been thinking about this stuff, just trying to figure out how we could sort of get a better understanding of this render. But you as you can see, guys, we actually have a better grasp of what's going on. The syncs basically have to line up, right? And notice that even when the cloth like just hangs and stays in one place, that there's still a lot of work going on in the background because this is real-time calculations, right? It's not just gonna stop because the picture freezed or we're showing the same thing. It's still gonna show. It's still gonna show what it shows, right? And then even with the wind, it's still the same thing, right? Nothing changes. So there you have it. And that's pretty much it, guys. So if you guys want to start on your journey with learning Vulkan, tutorial number 1 installs the Vulkan API on your Windows-based machine with a Vulkan-capable GPU. If you want to run the ray tracing stuff, you have to have a ray tracing capable GPU. This is not a ray tracing example, so even if your GPU is Vulkan capable but not ray tracing capable, you could still run the example. I highly recommend. So that's tutorial number 1, and then tutorial number 13 is installing all of these examples, right? Down here is where the ray tracing stuff is, right? If you you want to make sure you get an RTX and above for NVIDIA GPUs. I can't talk about the other vendors. But yeah, guys, I think I've pretty much beaten render function to death. There's nothing else I could talk about with this for now. I might start talking about other topics in the compute cloth. I kind of want to get into the buffer stuff, but I just don't, the storage buffer stuff, but I just don't know if it's necessarily I mean, there is some synchronization with it, but you know, I really just wanted to focus on the fences and the semaphores. So I'll see what I do, because I'm in the synchronization hell series, and I'll see what I do next. But I haven't forgotten about you guys. You know, I just want to make sure whenever I do a video, it's something of value, right? Oh, and this is the overlay. This is the overlay for all of this stuff. Yeah, I had a thing where it was wrapping, you know, it was wrapping the GFX in flight to 0, but I wanted to show the actual, you know, that there was something in flight, because there was a difference between the submits and the completes, right? But yeah, guys, this is it. So thank you for watching. Like, subscribe, you know the deal. Tell your friends. Have a great day. Bye.